This is a pneumatic actuator. It's an important part of many automatic process control systems. Actuators like this one convert air pressure into mechanical thrust that is used, for example, to position valves to control the flow of steam or water or other process variables. This is a different kind of pneumatic actuator. It also converts air pressure into mechanical motion that can be used, for example, to position dampers and louvers to control air flow. Pneumatic actuators are often used in conjunction with a positioner. A positioner is a device like this one that controls airflow to the actuator to ensure that the actuator produces motion. Typically, pneumatic actuators and positioners are rugged and dependable. But like any other piece of equipment, their parts can wear out from the rigors of around-the-clock use and may need to be replaced or adjusted from time to time. In this program, we're going to look at several different actuators and positioners to see what their component parts are, how they work, and how to adjust them. Part of your job as a technician is to install and adjust new actuators and positioners in your plant, or repair and adjust older devices. Now, you should already be familiar with some of the different types of pneumatic actuators and generally how they work. So in this part of the program, we'll watch as a technician disassembles some actuators. As we observe, we'll identify their parts and show you the kinds of wear or damage to look for when you work on similar actuators. Then, just for review, we'll briefly describe how each of the actuators operates. We'll start with a pneumatic diaphragm actuator. You may recall that in a diaphragm actuator, air pressure acts on a diaphragm in a pressure-tight case to develop thrust and produce motion, which is transferred by this metal rod to a final control element. In this case, this metal rod, which is called the actuator stem, was connected to the stem of a valve. The valve is not shown here. The actuator stem is coupled to the valve stem by this stem connector. Above the stem connector and threaded onto the actuator stem is this spring adjustment nut. This nut can be tightened or loosened to adjust the tension of a spring, which we'll be able to see as soon as the technician removes the nut. It's important in disassembling a diaphragm actuator like this one that the first step is to relieve the tension from the spring by loosening the spring adjustment nut, making it safe to disassemble the rest of the actuator. The bottom of the spring rests against a solid metal base plate called the spring seat. When the spring adjustment nut is tightened, it forces the spring seat against the spring, compressing the spring. Both the spring adjustment nut and the spring seat have been lubricated as a part of the routine maintenance procedures, so they do not bind when the spring adjustment nut is tightened. Once the spring adjustment nut and spring seat have been removed, the diaphragm casing can be taken apart. The diaphragm casing is divided into two sections or chambers, an upper chamber and a lower chamber. This actuator has a vent in the upper diaphragm casing which allows air to move freely in and out of the upper chamber. This vent should be cleaned as a part of the maintenance and must be kept clear so the flow of air is not blocked and the actuator can operate properly. The lower diaphragm casing of this actuator has an air port. Air is directed through this port to provide the force that makes this pneumatic diaphragm actuator work. Both sections of the diaphragm casing are bolted firmly together at the flange to form an airtight seal. If the flange on either the upper or lower casing is bent or cracked in any way, it must be repaired or replaced to ensure that the actuator doesn't develop air leaks. Also, the flanges must be clean and free of corrosion, which could also cause air leaks. Once the technician has inspected the flanges, He can now remove the entire diaphragm and stem assembly. Notice that the technician is extra careful when pulling the threaded portion of the actuator stem through the casing. He does this to avoid damaging the O-rings, which are used to form an airtight seal around the actuator stem. We'll look at the O-rings a little later, after the technician has disassembled more of this actuator. The technician can now separate the individual parts of the diaphragm and stem assembly. These include a bolt called the cap screw, a spacer, an upper diaphragm plate, the diaphragm, the lower diaphragm plate, and the actuator stem. The cap screw is screwed into the actuator stem to hold the entire assembly together. A metal spacer that is slid onto the cap screw during assembly limits how far the diaphragm assembly can move inside the diaphragm casing, as we will see when we describe how this actuator operates. The upper diaphragm plate serves as a solid backing for the flexible diaphragm and helps to keep the diaphragm from being damaged when air pressure is applied to it. The plate must be free of burrs that could damage the diaphragm. Any rough spots should be smoothed out with a fine-grade emery paper. The diaphragm is a flexible disc that is often molded from a synthetic rubber. It can dry out and split or crack from the rigors of regular use. If the diaphragm shows any indication of damage, it must be replaced. The lower diaphragm plate also provides solid support for the flexible diaphragm. In addition, the plate forces the diaphragm against the upper plate, squeezing it so that it forms an airtight seal around the actuator stem that prevents air from leaking from the lower diaphragm casing into the upper casing. The lower plate should also be free of any rough spots that could damage the diaphragm. The last part of the diaphragm and stem assembly is the actuator stem. The stem is continuously subjected to wear and stress as the actuator converts air pressure into motion. Sometimes this stress is severe enough to bend or break the actuator stem. Of course, when this happens, the stem would have to be replaced. After the technician has removed the diaphragm and stem assembly from the actuator casing, he can remove the spring. Now he can get to the O-rings by removing a retaining clip and pushing out the stem bushing. The O-rings are mounted inside the stem bushing, one at either end. As they are removed, they should be inspected for damage or wear. If they're worn or damaged, the O-rings must be replaced. Those are the main parts of a typical pneumatic diaphragm actuator and some of the kinds of wear or damage to look for as you take them apart. Of course, all pneumatic diaphragm actuators are not exactly the same. The ones you work on could vary somewhat from the ones shown here. So be sure to refer to the instruction manual for your actuator before taking it apart. Now that we've identified most of the parts of a common diaphragm actuator and seen some of the wear and damage to look for, let's go to a simplified illustration to see how this actuator works. This diaphragm actuator is similar to the one our technician was working on. Notice that the rubber diaphragm is sandwiched between the flanges of the upper and lower diaphragm casing to form an airtight seal that separates the upper chamber from the lower chamber. By changing the position of the internal mechanisms of this actuator, we can show how it works. In this actuator, air pressure is fed by an air line through the port into the lower chamber of the diaphragm casing. This air pressure lifts the diaphragm and stem assembly, causing mechanical motion. The amount of air pressure applied determines how much the assembly is lifted. The maximum amount of travel possible is determined by the size of the spacer. A larger spacer would reduce the amount of possible travel. A smaller spacer would increase the amount of possible travel. As air pressure is applied, the diaphragm and stem assembly is lifted up. In this case, the actuator stem would be connected to a valve stem, and the upward motion of the stems could open or close the valve depending on how the valve is designed. When the air pressure is removed, the spring returns the diaphragm and stem assembly to its original position. This actuator is classified as a single-acting diaphragm actuator because it has only one port for control air to enter, and control air pressure acts on only one side of this diaphragm. So essentially, all of the internal parts of the pneumatic diaphragm actuator serve one purpose: to move the stem of the actuator in response to changes in air pressure. This provides one way that we can operate control devices, such as valves or dampers. Another way to operate these control devices could be by using a piston actuator. We'll look at this kind of actuator when we return. But first, review the material in your text. The diaphragm actuator we just looked at is a very common type, and one that you'll probably see a lot. But the amount of motion that it can produce is limited. For this reason, the diaphragm actuator is not suitable for certain jobs. Another fairly common type of actuator is the piston actuator. Generally speaking, a piston actuator is more suitable for those jobs that require a greater amount of movement. Let's see what this kind of actuator looks like. In a piston actuator, air pressure acts on a piston in an airtight cylinder to develop thrust and produce movement, which is transferred by a metal rod to the final control element. In this case, the metal rod, which is the piston rod, is connected to a linkage arrangement that adjusts the position of louvers in an air duct to change air flow. The linkage and louvers are not shown here. The piston rod is connected to the final control element at this point. This U-shaped metal device is called a clevis. The end of the clevis has holes drilled in it for a metal pin to go through that attaches the clevis to linkage that connects it to the final control element. This allows movement of the linkage without binding. The main body of the piston actuator consists of a hollow rigid metal tube or cylinder and two end caps. The cylinder and end caps are connected by 4 long bolts that are threaded on both ends. Nuts are screwed on to the threaded bolts to hold the whole assembly together. This end cap has an anchor point that is used to fasten the actuator to a solid stationary object. This allows the entire actuator to pivot with the movement of the linkage without binding. The end cap also has an air port that allows air to enter or exit the cylinder. Generally, this end cap is removed first. Then, the piston rod is pulled to its fully extended position so that the cylinder can be removed. Notice that the inside bore of the cylinder is well lubricated. The main purpose of the lubricant is to protect the cylinder walls from rusting, although the lubricant also helps to reduce internal friction. The inside wall or bore of the cylinder must be very smooth and free of nicks, scratches, or rough spots. If there are any imperfections, they must be smoothed out so that the piston, which we will see next, isn't damaged when the actuator is operating. If imperfections in the bore cannot be repaired, the cylinder must be replaced. Now that the cylinder has been removed, the technician can separate the individual parts of the piston assembly. The piston is a cylindrical-shaped device that fits inside the cylinder bore. Changes in air pressure cause the piston to move, as we will see when we describe how this actuator operates. The piston assembly is mounted on the end of the piston rod and held together by these nuts. This piston has 2 cup subassemblies, which create an airtight seal between the piston and the walls of the cylinder. Each subassembly is comprised of essentially the same parts: a rigid metal disc called a flange that strengthens and supports the cup packing spring, a cup packing spring, which is a flexible slotted metal cup used as a form for the cup packing. It pushes the cup packing against the walls of the cylinder so that it forms an airtight seal that prevents air from leaking between the piston assembly and the cylinder wall. The cup packing is a stiff, cup-shaped piece of material, often made of leather. The cup leather is saturated with a high-temperature wax that seals the leather, making it airtight. Over a period of time, the leather can become brittle and crack and allow air to escape between the cup and the cylinder wall. When that happens, the cup packing must be replaced. A spacer fits into the center hole of the cup packing to protect the inside edge of the packing from damage during operation. Between the two cup assemblies is a rigid metal disc called the piston flange, which gives strength to the piston assembly. Inside the piston flange is an O-ring, which provides a seal between the piston assembly and the piston rod. If the O-ring is damaged or worn, it is replaced when maintenance is done on the actuator. Behind the second cup assembly is a spacer and washer. These last two parts of the piston assembly help to hold the piston assembly together and prevent it from coming in contact with the end cap. This end cap is designed to allow the piston rod to move through it without allowing air to escape around the rod, as we will see in a few minutes. Like the other end cap, this one has an air port that allows air to enter and exit the cylinder from this end. This end cap has a plug which can be replaced with a grease fitting so that the piston rod can be lubricated to prevent it from binding as it moves in and out. The piston rod is generally lubricated on a periodic basis. You may also notice another plug on the top end cap of the cylinder. Sometimes, between overhaul periods, the piston leathers can stick to the cylinder walls, causing a jerky operation. If this happens, this plug can be removed so that a recommended lubricant can be sprayed around the inside of the cylinder walls. Check your plant maintenance procedures to determine when routine lubrication is done on specific actuators in your plant. As the technician removes and disassembles the end cap, we can see that it has a flange packing cover, which is held in place by 4 small nuts and bolts. A cover holds the packing, which prevents air from leaking past the piston rod. This area is a common source of leaks in piston actuators. Leaks at this point can often be stopped by tightening the packing cover. If this does not stop the leak, the packing will have to be replaced. Those are the main parts of a typical pneumatic piston actuator and some of the kinds of wear and damage to look for. Generally, piston actuators are dismantled and cleaned on a regular schedule. Your plant maintenance procedures will usually contain this information. Although most piston actuators are basically similar, it's always a good idea to refer to the instruction manual for any actuator before taking it apart. Now that we've identified most of the parts of a common piston actuator and seen some of the wear and damage to look for, let's go to a simplified illustration to see how this actuator works. In this actuator, air pressure is applied through this air port, while the other port is simultaneously vented to atmosphere. The piston and piston rod assembly will move toward this end of the cylinder. The piston will continue to move until the air pressure on both sides of the piston equalizes, or until the piston reaches the end of the cylinder. Notice that the spacer and washer prevent the piston from touching the end cap. The piston can be moved to the other end of the actuator by applying air pressure through this port and venting air to atmosphere through this port. The nut on this side of the piston prevents the piston from touching the end cap on this end of the cylinder. So all of the internal parts of the pneumatic piston actuator serve one purpose: to move the piston rod in response to changes in air pressure. This produces a mechanical motion that can be used in a large variety of processes. Now, up to this point, we've looked at 2 actuators: a diaphragm actuator and a piston actuator. A lot of times, you'll see a positioner attached to these instruments. When we return, we'll find out what a positioner is used for, and we'll look at 2 common types. But for now, review the material in your text and answer the questions that go with it. So far, we've looked at a diaphragm and piston actuator and identified their parts. We've also described how they operate and some of the routine maintenance done to them. Now, in a process control loop, the air signal that tells these actuators how much to move sometimes comes directly from a controller. But this can create a problem. The change in air signal from a controller is often just a small change. The small change in a control signal may not be enough to cause the actuator to overcome forces holding the actuator and final control element in their present position. There are two forces that must be overcome in order for an actuator to accurately position a final control element. Friction, such as that caused by an actuator stem or control valve stem as it moves through seals and packing, and the resistance of a process variable moving against a final control element, such as liquid moving against a valve or gas moving against louvers. Now, if the amount of a process variable, such as the flow of a fluid, needs to be increased or decreased by a small amount, a controller will send out a signal proportional to the required change. If the signal is sent directly to an actuator, the signal may be too small to overcome the forces of friction and resistance, and an error in the system will not be corrected. In order to overcome this problem, an instrument called a positioner is used. Now, a positioner is designed to send enough air pressure to an actuator to move a final control element, regardless of how small the control signal is. Once the final control element is in the correct position, the positioner is designed to hold it in that position. You see, the positioner knows when the actuator has moved the final control element to the correct position because there is a mechanical feedback link between the actuator and positioner. You'll see the importance of feedback in controlling actuator travel as we explain the operation of positioners. In this part of the program, we're going to look at two types of positioners: a force balance positioner and a motion balance positioner. We'll start with the force balance positioner. First, we'll identify the self-balancing mechanisms and describe how they work in relation to a control signal from a controller and the action of an actuator. As we go along, we'll also identify some of the various parts of the positioner. Finally, we'll describe just why this is a force balance positioner. This is a fairly simple positioner and one that is quite common in industrial applications. It's a self-balancing device, as are many pneumatic instruments. As you may remember, self-balancing instruments have an input, error detector, and output or balancing mechanism. The input mechanism for this positioner is this bellows. The error detector mechanism is this pilot valve. And the output or balancing mechanism is this spring with its associated beams and linkages. Let's see how these self-balancing mechanisms work. And as we observe, we'll identify the various parts of the positioner. When the positioner receives a control air pressure signal from a controller, the control air enters the input bellows. Remember, this signal from the controller is meant to correct an error in a process variable. The bellows converts the force of the control air pressure into motion by expanding when the control signal is increased and contracting when the control signal is reduced. As the bellows expands and contracts, it pivots the balance beam, which moves the pilot valve stem. Now, it's the pilot valve that directs air pressure to an actuator. We can use a simplified illustration to see how. This illustration of the pilot valve shows some of its inside parts, so we can see how it works. Here we can see that the pilot valve has 3 air lines connected to it. The middle line is usually connected to supply air from the plant's compressed air system. In this example, the other 2 lines are connected to opposite sides of a piston actuator. There is also a valve stem that has 2 discs on it that moves inside the valve body. The 2 discs serve as plugs, which allow air to enter or leave the actuator through these air pressure lines that are connected to the actuator. Air that leaves the actuator is exhausted to the pilot valve and out through here, where the valve stem moves through the valve body. Now let's see how these mechanisms work to position the actuator. Assume that the control air increases. This causes the bellows to expand and push up on the balance beam. As the balance beam moves up, it lifts the pilot valve stem. This opens both output ports, allowing supply air to flow through the pilot valve and out the upper air port to the piston actuator. At the same time, air is bled out through the lower air port of the piston actuator and out through the lower part of the pilot valve. This causes the piston and piston rod to move. If control air decreases, the bellows contracts, lowering the balance beam and pilot valve stem. This reverses the flow of supply air to and from the piston actuator, moving the piston and piston rod in the other direction. Now, so far we've seen how a positioner responds to control air by directing supply air to a piston actuator to move the piston and piston rod either up or down. But the purpose of a positioner is to position the actuator according to the control signal it receives from the controller. Now, sometimes this may be all the way up or all the way down, but sometimes it will also be at various positions in between. This is where the feedback that we mentioned earlier comes in. The piston actuator is connected to a series of mechanical links that move as the piston rod moves. These links are connected to the positioner at this drive arm. In this positioner, this drive arm and gear meshes with a smaller gear. As the piston rod and its connecting linkage moves, it rotates this drive arm and these gears. The smaller gear is mounted to a shaft that extends through the positioner case and is connected to a cam. When the piston rod and its connecting linkage rotate the drive arm, it causes the cam to rotate. So this gets us back inside the positioner, where we can describe the rest of the balancing mechanism. When the cam rotates, it pushes against a little roller, which is called a cam follower. This roller, or cam follower, is part of the device which is called a spring beam assembly. When the cam rotates, it pushes against the cam follower, which causes the spring beam assembly to rotate. The spring beam assembly is different than the balance beam. Both beams are connected by a spring, so when the spring beam assembly moves, the motion is converted to a force, which is the force of this spring pulling against the balance beam. All of these parts, the drive arm and gears, the cam, cam follower, spring beam assembly, and spring, make up the balancing mechanism of this positioner. Sometimes it is also referred to as the feedback mechanism, because information about the position of the actuator is fed back through these parts to ensure that the actuator is positioned where it is intended to be. Now let's go back to our illustration to see how these balancing mechanisms work in relation to the input and error detecting mechanisms and the actuator. Assume again that control air to the bellows increases. This causes the bellows to expand and push up on the balance beam. As the balance beam moves up, it lifts the pilot stem, which simultaneously directs supply air to one side of the actuator and allows air to bleed out of the other side of the actuator. Now the piston in a piston actuator should move a specific amount for the amount of force exerted by control air on the bellows. If the control air pressure is greater, the piston will move more. If the control air is less, the piston will move less. But as long as the pilot valve directs air to the actuator and allows air to bleed off, the piston will continue to move. This is where the feedback balancing mechanisms come into play. As the piston and piston rod moves, the linkage that connects the piston rod to the drive arm of the positioner also moves. This rotates the drive arm and gears, the cam, and the spring beam assembly. As the spring beam assembly rotates, it pulls down on the spring, which pulls down on the balance beam. This downward force on the balance beam counters the upward force in the bellows. When the downward force balances the upward force, the pilot valve closes so that no more air enters or leaves the actuator. This stops the piston from moving and holds it in position until the controller sends a new signal to the positioner. So, in this positioner, balance is achieved by two opposing forces: the upward force caused by the expansion of the bellows in relation to the signal from a controller, and the downward force caused by the spring in relation to the position of the actuator. This is basically how a force balance instrument works. That is, a force balance instrument works on the principle of achieving a balance between two forces. In a few minutes, we'll be looking at another positioner called a motion balance positioner that works on the principle of achieving balance between two opposing motions. For now, though, turn to your text and review the parts and operation of the force balance positioner that we just looked at. You may remember that the function of a pneumatic positioner is to respond to a signal from a controller by regulating airflow to move an actuator to a specific position. If the actuator does not move the amount specified by the signal from the controller, the positioner will compensate by allowing more air to flow to the actuator until it does move to the proper position. Then the positioner will shut off the airflow to stop the actuator and hold it in place. The way the positioner does this is by balancing an input with an output. For example, the force balance positioner that we just looked at balanced an input force caused by the expansion of a bellows in relation to a signal from a controller with an output force caused by a spring in relation to the position of an actuator. In other words, a force balance positioner works by balancing two forces, and balance is only achieved when the actuator has moved the required amount. Now, while some positioners work on the principle of balancing forces, others work on the principle of balancing motions. These are called motion balance positioners, which we're going to look at now. We'll approach this kind of positioner in the same manner that we looked at the force balance positioner. First, we'll identify the self-balancing mechanisms and describe how they work in relation to a control signal from a controller and the action of an actuator. And as we go along, we'll also identify some of the various parts of the positioner. Finally, we'll describe just why this is a motion balance positioner. Now, although this positioner looks quite different than the force balance positioner, it still has the input, error detector, and output mechanisms present in all self-balancing instruments. In this positioner, the input mechanism is this bellows. The error detector mechanism is this flapper nozzle arrangement. And combined with it, but hidden inside this part of the positioner case, is a pilot valve type of device. The flapper nozzle arrangement, when combined with the pilot valve, is called a pneumatic relay. The output or balancing mechanism is this cam and cam follower with its associated linkage. Let's see how these self-balancing mechanisms work, and as we observe, we'll identify the various parts of the positioner. When the positioner receives a control air pressure signal from a controller, the control air enters the input bellows. Remember, as we said before, that this signal from the controller is meant to correct an error in the process variable. The bellows converts the force of the control air pressure into motion by expanding when the control signal is increased and contracting when the control signal is reduced. As the bellows expands and contracts, it pivots this balance beam. Now, this balance beam is a little different than the one we saw in the force balance positioner. As you can see, it's in the shape of a half circle rather than a straight bar. And with this positioner, when the bellows expands and contracts, it pivots the balance beam, which moves the flapper arrangement either closer to or farther away from this nozzle. A unique aspect about this balance beam and flapper arrangement is that the flapper can be positioned so the positioner responds in different ways. For example, with the flapper on this side of the balance beam, when the bellows expands and the beam moves, it causes the flapper to move away from the nozzle. On the other hand, with the flapper moved over to this side of the balance beam, when the bellows expands and the beam moves, it causes the flapper to move closer to the nozzle. There's another unique aspect about this flapper nozzle arrangement, and that is that it's combined with a pilot valve type of mechanism. It's this flapper nozzle pilot valve combination, or relay, that directs air pressure to an actuator. We'll use a simplified illustration to see how. This illustration shows some of the inside parts of the relay. Let's identify some of these parts and then see how they work to regulate airflow to the actuator. Here we can see the nozzle extending out of the relay compartment. The back pressure chamber is located here. It will expand or contract depending on the position of the flapper. Under normal balance conditions, some air always escapes through the nozzle. However, when the flapper is moved closer to the nozzle, less air escapes, and a pressure or back pressure, as it is often called, builds up inside this chamber. We will look more closely at why changes in pressure in the back pressure chamber are important to the operation of the relay a little bit later. Now, at the other end of the assembly is the supply air chamber. Notice that the supply air is also directed through this port to the nozzle back pressure chamber. This part of the relay represents the plug portion of the pilot valve. The plug is connected to a spring at this end. When the plug is moved, it opens or closes these two restrictions. The part that connects the pilot valve mechanism to the back pressure chamber is this solid piece of metal. Notice that it has an air port through it. This allows air to bleed out of the actuator and through the relay, as we'll see shortly. At either end of this metal piece are diaphragms that divide this inner compartment of the relay into three chambers. This chamber is the nozzle back pressure chamber. This chamber directs air to and from the actuator. And this chamber vents air to atmosphere. Now that we've identified the major parts of this relay, let's see how they work to position the actuator. Assume that control air increases. This causes the bellows to expand, moving the balance beam and positioning the flapper closer to the nozzle. When the flapper is closer to the nozzle, pressure in the nozzle back pressure chamber increases until there is a sufficient back pressure against the upper diaphragm to push down on this metal part, which in turn pushes down on the plug. As the plug is pushed down, it opens this restriction, allowing air to flow through the restriction and out to the actuator. This causes the actuator to move. If control air decreases, the bellows contracts, moving the balance beam and positioning the flapper away from the nozzle. With the flapper away from the nozzle, more air is allowed to escape through the nozzle, reducing the pressure in the back pressure chamber. If the pressure in this chamber decreases so that it's less than the pressure in this chamber, the metal part will be pushed in the other direction. At the same time, a spring pushes the plug up, closing the restriction and shutting off the flow of supply air to the actuator. If the pressure in this chamber drops enough, the metal piece will be pushed up so that this restriction is opened. This would allow air from the actuator to bleed back through the relay and to atmosphere. When this happens, of course, the actuator spring returns the actuator stem to its original position. The actuator stem is connected to a series of linkages that move as the actuator stem moves. These linkages are connected to the positioner at this drive arm. In this positioner, the drive arm is mounted to a shaft that extends through the positioner case and is connected to a cam. When the actuator stem and its connecting linkage rotates the drive arm, it causes the cam to rotate also. When the cam rotates, it pushes against a cam follower. The cam follower in this positioner is attached to the balance beam. So, when the cam rotates, it pushes against the cam follower, which causes the balance beam to move. The drive arm, the cam, and the cam follower make up the balancing mechanism of this positioner. As in the force balance positioner, the balancing mechanism is sometimes referred to as the feedback mechanism, because information about the position of the actuator is fed back through these parts to ensure that the actuator is positioned where it is intended to be. Let's go back to our illustration to see how these balancing mechanisms work in relation to the input and error detecting mechanisms and the actuator. Assume again that the control air to the bellows increases. This causes the bellows to expand, moving the flapper closer to the nozzle. And as we saw earlier, this causes the parts inside the relay to move so that supply air is directed to the actuator. Now, the diaphragm assembly in this actuator should move a specific amount for the amount of control air applied to the input bellows. But as long as the relay directs air to the actuator diaphragm assembly will continue to move until it reaches full travel. This is where the feedback balancing mechanisms come into play. As the actuator assembly moves, the linkage that connects the actuator stem to the drive arm of the positioner also moves. This rotates the drive arm and cam. As the cam rotates, it pushes on the cam follower, causing the balance beam to move. This motion of the balance beam counters the motion caused by the expansion of the bellows and moves the flapper away from the nozzle. This in turn changes the pressure in the nozzle back pressure compartment, which also allows the relay plug to begin to close. When the motion of the cam balances the motion of the bellows, the flapper is positioned so that the relay plug shuts off the flow of supply air to the actuator. This stops the diaphragm assembly from moving and holds it in position until the controller sends a new signal to the positioner. So, in this positioner, balance is achieved by two opposing motions: the motion of the balance beam caused by the expansion of the bellows and the motion of the balance beam caused by the rotation of the cam. This is basically how a motion-balanced instrument works. That is, a motion balance instrument works on the principle of achieving a balance between two motions. Okay. Well, we've identified the parts of a common diaphragm and piston actuator and saw generally how both actuators operate. And we looked at the parts for a common force balance and motion balance positioner and saw generally how they operate. When we continue, we'll look at how a force balance positioner and a piston actuator are adjusted before being put back into service. But first, review your text. If you have any questions, be sure to discuss them with your instructor. After maintenance has been performed on actuators and positioners, they can be remounted at their original field locations. But before they can be put back into service, they have to be adjusted for their specific applications. What we're going to do now is observe as another technician makes adjustments to a force balance positioner with a piston actuator that was recently repaired and returned to its field location. Later, we'll observe as he adjusts the same kind of positioner with a diaphragm actuator. The actuator and positioner in this application is used to position louvers that regulate the flow of air through a large duct. The duct isn't carrying any air right now because it's been taken offline and shut off from other systems. This way, the technician can make adjustments without affecting other processes down the line. Both the piston actuator and the positioner are enclosed in a metal shell, similar to the one we saw back in the shop. Before beginning work on an actuator like this one, it's a good idea to shut off the flow of supply air to the positioner. This locks in any air pressure in the piston cylinder and prevents the piston and actuator linkage from moving unexpectedly. Some mechanisms like this have mechanical locks that keep it from moving. The purpose of locking the instruments in place is to ensure the technician's safety until he's ready to make his adjustments. With this done, the technician can get to the actuator and positioner and be reasonably certain that the mechanisms won't move until he wants them to. Some of the tools the technician will be using to adjust these instruments include the usual assortment of screwdrivers, wrenches, and pliers, and a manual loading instrument, like this one. The manual loader is hooked up to an air supply and is also connected to the positioner in place of control air. This way, the manual loader will be supplying controlled amounts of air to the positioner. This instrument has a regulator that allows the technician to control the air pressure going to the positioner. It also has an accurate pressure gauge that indicates how much air pressure is being supplied to the positioner at any given time. The instrument you use in your work may look different than this one, but it serves the same purpose. This instrument temporarily replaces a controller and is used to manipulate the flow of control air to the positioner so that the technician can make adjustments at different control air pressures. Before this instrument can be connected to the positioner and the plant air supply, the regulator should be turned completely counterclockwise so that no air flows through the instrument until it is needed. Next, the technician locates a source of supply air and closes it off so he can connect the manual loader to the air supply. Then, the technician connects one air line from the manual loader to the air supply and another line from the loader to the control air input of the positioner. Once the manual loader is properly connected, the supply air can be opened up to allow air to flow to the instrument. At this point, if the regulator wasn't turned off, the supply air would flow through it to the positioner, where a sudden surge of air pressure could damage the input bellows. After the air to the instrument is turned on, the supply air to the positioner can also be turned back on. At this point, because the manual loader is supplying no control air to the positioner, the force of the positioner spring moves the pilot valve so supply air goes into one end of the actuator and air at the other end of the actuator bleeds out through the pilot valve. This causes the piston to move down to its shut position and at the same time shut the louvers. The technician is now ready to start checking and adjusting the positioner. The steps we're going to observe him perform apply to that specific actuator and positioner. Since your instruments may vary somewhat from these, even though they may look very similar, you should refer to the manufacturer's recommended procedures before making any adjustments. Let's go back to our technician and observe him as he makes his checks and adjustments. Now, the range of this positioner is 3 psi for its minimum input air pressure to 27 psi at its maximum input air pressure. So the first step is to set the control air pressure from the manual loader to the positioner at 3 psi. So with the manual loader supplying a control air pressure of 3 psi, the piston and louvers should remain in a shut position. With control air to the positioner at 3 psi, the cam should indicate 0. Then with his finger lightly touching the edge of the cam, the technician increases the loading pressure just slightly until the manual loader indicates 3.5 psi. At this pressure, the technician should be able to feel the cam move just slightly, indicating that the piston in the actuator is beginning to move away from the shut position, partially opening the louvers. If the cam doesn't move, the zero adjustment nut is turned. Then the cam is checked again at 3 psi and 3.5 psi. This procedure is repeated until the desired results are achieved. The technician proceeds by increasing the control air loading pressure to 27 psi. This is the fully opened loading pressure for this positioner. In your plant, or for other applications, the maximum loading pressure could be 15 psi or any number of other maximum pressures, depending on the instrument and the manufacturer's specifications. When the loading pressure is at 27 psi, the cam should indicate its maximum travel, or in this case, 10. If it doesn't, lift up on the balance beam. If the cam moves, then the piston and louvers aren't at their fully open positions, and the positioner needs to be adjusted so that the cam indicates 10. Even if the cam doesn't move when the beam is lifted, the cam should still indicate 10. This adjustment is made by loosening the range adjustment and moving it along the spring beam until the cam indicates 10. Then lift the balance beam again to make sure the cam doesn't move, indicating that the piston and louvers are indeed fully opened. With the control air pressure at 27 psi and the cam reading 10, the piston and louvers should both be fully opened. After performing all of the checks and adjustments that we just saw, the procedures should be repeated to be sure that all of the adjustments were correct and the instruments are working properly. Then the manual loader can be disconnected, carefully following the safety procedures used when the instrument was connected. Finally, the positioner can be reconnected to the control air supply and all the covers remounted. Before the positioner and actuator is put back online, an operator at the manual transfer station should apply both 3 psi and 27 psi to the positioner to make sure it operates properly in the manual control mode. Then the system can be put back online and switched to the automatic mode. Well, that takes care of checking and adjusting a positioner with a piston actuator. Take some time now to review the material in your text. When we return, you'll see how a diaphragm actuator is stroked and then how to make adjustments to the same kind of force balance positioner with the diaphragm actuator. In just a few seconds, we're going to watch a technician attach an actuator stem to a valve stem. The procedure used to attach these two stems together is commonly called stroking. But before we do that, it would be a good idea to remind yourself of something. The procedures we'll be watching here are correct, but we'll only be looking at one kind of actuator and one kind of positioner. And even if another actuator looks similar, the way it operates as well as the way it is stroked can be different. And in addition, the procedures for adjusting these instruments can vary from plant to plant. So before you begin to adjust any instrument, consult your plant procedures and the manufacturer's manual for the exact procedures to follow. You may find that many of the procedures are similar to the ones we'll see here, but check anyway. Now, with that in mind, let's go into the plant to see how a single-acting diaphragm actuator can be stroked and how the positioner attached to it is adjusted. The actuator and positioner in this application is used to position a valve that regulates the flow of water in a pipe. The actuator has been mounted on the valve casing, and air from the loader is connected beneath the lower diaphragm casing. So, this is an air-to-lift and spring-to-return diaphragm actuator. Air has been introduced to the diaphragm, so the actuator is in the open position. What needs to be done now is to connect the actuator stem to the valve stem and adjust an indicator plate. With the actuator in the open position, the actuator stem has been lifted away from a hex nut that has been screwed on to the valve stem. Before the two stems can be connected, we have to be sure that the valve is seated. In other words, the valve must be closed. This is done by, first, placing a flat metal bar between the hex nut and the actuator stem. Then, shut off the air to the actuator and remove the air line to unload the air inside the actuator. As the air is unloaded, the actuator spring pushes the actuator stem down onto the hex nut, pushing down on the valve stem and seating the valve. Then the air is reapplied to the actuator so that the actuator stem is completely raised to the open position. With the actuator stem at its highest position and the valve stem at its lowest position, we're ready to line up the stem travel indicator. Here you can see the long hex nut, travel indicator plate, and small hex nut mounted on the valve stem. Over to the right, on the yoke of the actuator, is the travel indicator scale. What we want to do now is raise the travel indicator plate so that it is lined up with the lowest marking on the indicator scale. To do this, raise the long hex nut and the travel indicator plate. Then, raise the small hex nut until it supports the travel indicator plate at the low scale marking. Since the valve is seated at its lowest position, if the travel indicator plate on the valve stem is set across from the low scale mark, then whenever the valve is closed, the travel indicator will read 0 or closed. Next, we want to raise the valve up so that the indicator plate is lined up across from the high scale marking. To do this, raise the long hex nut until the bottom edge of the nut is lined up with the high scale marking on the travel indicator scale. As you do this, the long hex nut screws onto the actuator stem, securely connecting the actuator and valve stems. Be sure not to move the small hex nut that is supporting the travel indicator plate across from the low scale mark. Then, again, without touching the small hex nut, turn the valve stem with a wrench. Be sure to apply the wrench only to the flat part of the valve stem so you don't damage the threaded part of the stem. What we're doing by turning the valve stem is screwing the valve stem up into the long hex nut that is connecting the actuator stem with the valve stem. In doing this, we are opening the valve. Continue raising the valve in this manner until the travel indicator plate on the valve stem is lined up with the high mark on the travel indicator scale. You should understand that we did not change the position of the indicator plate on the valve stem. Instead, we connected the valve stem to the actuator stem by raising the valve to its fully opened position. After the valve has been raised so that the indicator plate on the valve stem is lined up across from the high mark on the travel indicator scale, tighten the two hex nuts together. Once the two nuts are tightly secured, we can release the air pressure that is holding the actuator diaphragm up so that the actuator stem, valve stem, and valve can be lowered to the closed position. In the closed position, the indicator plate should indicate the lowest or closed position on the indicator scale. To make sure that the actuator and valve were stroked properly, reapply the air supply to the actuator so that the valve opens all the way up. The indicator plate on the valve stem should be raised up so that it indicates the highest or open position on the indicator scale. Once the actuator has been run through a complete cycle and the travel is correct, then the manual loader can be disconnected from the actuator and the air supply line from the positioner reconnected. At this point, the manual loader is connected to the positioner. Then the positioner is adjusted so that with an air pressure to the positioner of 27 psi, the actuator opens the valve all the way. And for an air pressure of 3 psi, the actuator closes the valve completely. The adjustments are the same procedures that the technician followed when we observed him adjusting the positioner for the piston actuator, so we won't repeat them here.